Hi everyone. Okay, so in this session, I'm going to continue our lecture on the moment array theorem. So basically, in the previous lecture, I have explained in detail on the moment array theorems, and in this session, we will use the moment array theorem to solve a problem with regards to the displacement and rotation in a beam. Okay, so without further ado, let's start with the example one. Okay, so in the example, we have a cantilever beam that's loaded by the point load at point C. So the amount is equal to 10 kilonewton. And given that the E and the I value for the beam. Okay, so basically we have seen that the procedure of analysis for this method involve three steps. Okay, the first step is to draw the MEI diagram. Followed by the second step to draw the elastic curve diagram or the deformation shape of the diagram of the beam. And the third step is apply the moment array theorems, either theorem 1 or theorem 2. Sometimes we need to use both of a theorem. Okay, so we will look into this if I'm not mistaken, example 3 or 4 like that. Okay, so let's focus on the example 1. Okay, so let's look on the solution for this particular example. Basically, to draw the MEI diagram, you need to get the equation of moment. Okay, so how to get the equation of moment is by using the cut section method that you have learned in a previous subject, which is solid mechanics. Okay, so how to use a cut section method? So I don't want to explain in detail how to use it. You may open your book on the solid mechanics and recall what you have learned on that. Okay, so okay, the equation of moment for this particular cantilever beam is equal to negative 10x. Okay, so by using this equation of moment, you can draw this particular MEI diagram. Okay, the one thing that I want to highlight here. So basically, the bending moment diagram is different from the MEI diagram. So for the bending moment diagram, we only have a M, okay, against the X, okay, means the span of a beam. While in this MEI diagram, we have the vertical axis is represented by the MEI value. Okay, so where you can see that here, this is a value that we have calculated from the equation of moment. Okay, so at x equal to 0, at x equal to 5 and x equal to 10. So the value is 0, negative 50 and negative 100 respectively. So by using this value, you can plot the MEI diagram. So you can see that here at point B, so the MEI value is equal to negative 50 over EI. At x equal to 10, so the value of MEI is equal to negative 100 over EI. Okay, so once you have obtained this particular MEI diagram, you can proceed to the second step. So later we will return to this diagram in order to get the value of angle at point B and C. Okay, so okay. So in this example, you can see that we have a cantilever beam that loaded by the point load. So this this beam will deflect downward, and you can see here, or you can grab your ruler and try to hold one end and try to push at a free hand. You can see that that is the shape of you will get the same shape of what you can see in the slide in the red line here. Okay, so the next step, we will draw the tangent line and the angle, so to indicate the situation. Okay, and once we have this particular complete diagram of elastic curve with the angle in the elastic curve, so we will take out a few equations. Okay, so you need to take out an equation. You need to formulate a equation from the elastic curve diagram. Okay, okay. So once you have drawn the elastic curve diagram, okay, in a red color here, as you can see in this red color, you need to draw the tangent line. Okay, so they have three tangent lines that you need to draw here. First is tangent line A, okay, tangent line B, and tangent line C. So why we need those tangent lines? Because in this problem, we want to get the slope at point B and at a point C. Okay, so that's why we need to draw the tangent line at B and tangent lines at C. So tangent line at A is normally assist us, okay, and normally draw based on the tangent line at support. Okay, so in most situations, you will see in example 2 up to example 4 later on. So most of a tangent line at support must be drawn in order to help to calculate the displacement and rotation in the beam. In this case, we have a fixed support at point A, so you need to use this particular point A as one of your tangent lines. Okay, so the tangent line at A is a straight, so the point is at A. Okay, so the point of touch for this tangent line is at A. So the touch point for the tangent line at B is the point B. The touch point of a tangent line for C is point C. Okay, so accordingly is okay. So once we have drawn the tangent lines, okay, the intended tangent lines, so you can draw the or you can indicate the angle of angle at B and angle at C. Okay, so this angle at B and angle at C is the angle that we want to determine. Okay, how to draw this angle? Okay, so first you need to draw the horizontal line that parallel to the beam line. Okay, so this line, and you can see that the angle B is measured from this particular horizontal line that you just drawn towards the tangent line B. Okay, same goes for the point C. So you need to draw a horizontal line that parallel to the beam line. Okay, or in this case parallel to tangent line also. Okay, so and the angle C is measured from horizontal line here, okay, towards the tangent C. Okay, so once you have indicated the angle B and angle C in the curve diagram, in the elastic curve diagram, okay, you can proceed to indicate the relative angle. So the relative angle here I'm refer to the angle between points. For instance, that you can see in this diagram, theta BA and theta CA. Okay, how to indicate this particular relative angle? Okay, let's look on the theta BA. Okay, so the theta BA can be obtained by draw the angle between the tangent A and the tangent B. Okay, so the direction of angle is from A to B. So you can see the A to B. Okay, for C, theta CA, so the angle is drawn from A to C in a clockwise direction. Okay, so in a clockwise direction. So this will give a negative value for the angle. Okay, since it's in a clockwise direction that I have explained in the previous lecture. So the counterclockwise will give a positive value. The clockwise will give a negative value. Okay, so once you have completed to indicate all the angles in the elastic curve diagram, okay, you can check out equation. Okay, so you will use that particular equation to calculate the angle at B and angle at C. Okay, let's move on the next slide. Okay, since this is about the slope, so we need to use the first theorem. Okay, so the first theorem is about the slope. The second theorem is about the deflection or the vertical deviations in the beam. Okay, so since we have established the elastic curve diagram and the MEI diagram, so we will use both of these diagram to calculate the angle at point B and at point C. Okay, so this is the diagram that we have seen just now in the previous slides. We carry over this diagram to this slide. Okay, so based on this elastic curve diagram, you can see that the theta b is equal to theta ba. Okay, so basically this theta b cannot be calculated unless you relate this theta b with respect to theta ba based on this elastic diagram. In other words, you can't to identify this theta b without this particular elastic curve diagram. Okay, so you can see that this theta b is equal to this particular theta ba in this particular elastic curve diagram. Okay, similarly for the theta c, okay, based on this elastic diagram, you can see that angle theta c is equal to theta ca, because in this case you can see that this angle of theta ca is from horizontal towards tangent c. Similarly, for angle C from horizontal to tangent C. Okay, for the point B, okay, so theta BA is from horizontal towards tangent B. Meanwhile, theta B is from horizontal towards tangent B. Okay, so once we have established this particular equation, okay, so you can use the MEI diagram to calculate the angle at B and angle at C. Let's relook on the angle at B. So we have defined that angle B is equal to angle BA. Okay, so this angle BA can be simply obtained from this MEI diagram. Okay, how to get that? Okay, let's look on the solution here. Okay, so theta BA, you can see that here in between the region is the limit is B to A. Okay, so based on this MEI diagram. Okay, so meaning that you need to find out the area of this particular shaded area. So B to A. Okay, so and you can, based on this solution, you can see that this particular area has been divided into two shapes, okay, which is a rectangular and a triangular. So you can see that the first term here is referred to the rectangular. The second term here is referred to the triangular. Okay, so this is the area of a rectangular. This is the area of a triangular. Okay, so and you can see that the area of a rectangular here is 50 over EI multiplied with 5 meter. Okay, and for the triangular, so the area is given by half of 50 over EI multiplied by 5 meter. Okay, so and simplify this, you will get the this equation, and further substitute the value of flexural rigidity, the EI value. So you will get that the angles of BA is equal to negative 0.00521 radian. So basically, we have defined that theta BA is equal to theta B. So and this is a value of theta B, okay, angle at point B. Okay, so move to point C. So we have defined that theta C equal to theta CA. Okay, so meaning that you need to calculate the entire area of this triangle. Okay, because you can see that this is about the CA. So from point C to A, which is the limit is from 0 to 10. Okay, so it's covered the entire diagram, MEI diagram. Okay, so meaning that you need to get the area of this particular triangle. Okay, so and by calculating this particular area, you can see that the equation is equal to half multiplied by negative 100 over EI multiplied with the 10 meter. So 10 meter is this one. So negative 100 EI is this one. Okay, so the height of this triangle. Okay, simplified. So you can see that the angle at C is equal to negative 0.00694 radian. So and both of value is negative. So indicates that the angle is measured in a clockwise from point A. Okay, so let's move on to the second example. Okay, so in this examples, we still deal with the cantilever beam, but you can see that the sections is different from AB to BC. the section area, means that the I is different from AB to BC, and we have a applied point moment which is equal to 500 Newton meter. Okay, so given that the E equal to 200 GPa, so in these examples we need to calculate the deflection at point B and at point C. Okay, at point B and at point C. Okay, so without further ado, let's discuss the solution in this particular example. Okay, so the step remain the same. So you need to draw the MEI diagram. The second step, you need to draw the elastic curve diagram, and the last step, which is the third step, you need to apply the moment area theorem. Okay, so in this problem, since we need to calculate the deflection of a beam, so we need to apply the second theorem for the moment area method. Okay, as usual, you need to get the equation of moment before you can draw the MEI diagram. Okay, so I don't want to explain in detail how to get the equation of moment, since you just required to use the moment, the cut section method. Okay, so basically what you can see in the first step, they have two diagrams. So this is a bending moment diagram. So this is a MEI diagram. But in this particular example, I mean that in this topic, so we don't want to use the normal BMD. Okay, we want to use the MEI diagram. Okay, since in this case the section area from AB to B is different, where you can see that the section area of AB is 2 times, not the section area, the second moment area of beam from AB to BC is 2 times. Okay, AB is 2 times to the BC. Okay, so you can see that by dividing the moment with the EI, the flexural rigidity. Okay, so and you can see that the shape of bending moment diagram change to this particular shape of MEI diagram. So how this happens? By looking on this particular sentence. Okay, so where we have defined that the IAB is 2 times than the IBC, so we make it IBC as our single I. So and that's why in this case we have a 2 EI, and for BC we have a EI only. Okay, so by dividing the moment value with respect of to this value of 2 EI, so this 500 become 250 divided by EIBC. Meanwhile, for the section B to C, so 500 divided by EI, so the shape remained the same. Okay, so you can see that the shape from AB have changed from the bending moment diagram towards the MEI diagram. Okay, so I hope that you can figure out of this changing. Okay, so where in the example 1, you can see that the bending moment diagram shape is similar to the MEI diagram because there is no change in the cross-section area of a beam. Okay. Okay, so the next step, you need to draw the elastic curve diagram. So what you can see here, this is the elastic curve diagram. Since the point moments applied is in a counterclockwise, so this beam will deflect in counterclockwise. Okay, so since in this problem we need to calculate the vertical deflection at point B and at point C, so you need to draw the tangent lines for B and for point C. Okay, so as usual, as an example, once we need to use the tangent line from support. Okay, so the tangent line from support, you can see that here. So basically in horizontal, and tangent line B, you can using your ruler, and by touching only at a point B, so you will get the tangent line at for the B, and the same for the point C. Okay, by using the ruler, you can get the tangent line for C. Okay, so from the elastic curve diagram, okay, how to indicate the TBA and the TCA. Okay, basically this is a original shape, okay, undeformed shape of a beam. So the blue color lines of the blue curve is indicate the deformation shape of a beam. Okay, so from this point to point B, okay, so this length, and for the C from this point to this point C is a deflection of point B, and this is deflection for point C. Okay. Okay, since this particular delta B and delta C cannot be simply calculated based on the MEI diagram, so you need to get one relation. Okay, for example, here we have defined that delta B, which is a displacement at the point B, is equal to TBA, and also for the displacement at the point C is equal to TCA. So why we can define delta B is equal to this rule TBA, and why we can define that delta C equal to TCA. Okay, let's relook on the point B. So TBA is about the tangent line B and tangent line A. So which is by recall in the previous lecture. So the vertical derivation is defined as a distance between tangent line towards the deflected point. So in this case, we deal between the 2 points, okay, because in the moment error method, the principal concept is when you want to get the displacement or rotation at specific point, you can't only use 2 tangent lines for a specific point that you want to calculate. Okay, so for instance here, we want to get the displacement at a point B, so only 2 tangent will get involved. Okay, the tangent A, tangent line A, and the tangent line B. Okay, so basically the vertical derivation is referred to the tangent line towards the deflected point. So TBA can be draw by draw a line from the tangent line A to point B. Okay, so this we name it as a TBA. Okay, meanwhile for the TCA, so you can draw one vertical line from tangent lines. Okay, so in this case, tangent line A towards the deflected point. So the deflected point is referred to point C. So this vertical derivation we name it as a TCA. And basically, this TCA is equal to delta C, and this TBA is equal to delta B. Okay, so we have done for the elastic curve. Let's we use that particular equations into the second theorem. Okay, so this is a second theorem. Okay, so that we have seen in the first lecture for this particular topic. Okay, and we carry over the diagram into this slide. Okay, the MEI diagram and the elastic curve diagram. And we have defined that delta B is equal to TBA and delta C is equal to TCA from the elastic curve diagram. Okay, so let's we look on the delta B. Because how we can use this particular second theorem to calculate the displacement at the point B. Okay, so let's we focus on this TBA. Okay, so TBA basically is the limit from A to B. So by looking on this MEI diagram, so the area covered is from A to point B. So in other words, you just need to consider this shaded area, okay, in order to get the value of a TBA. Okay, one more thing, in this equation we have X bar. Okay, so this particular X bar can be obtained by looking on 2 points, okay, that I have defined in the first lecture. This X bar is based on the first alphabet. Okay, you need to look on the first alphabet for the displacement at point B, so which is a TBA. The first alphabet is a B. For displacement at point C, for TCA, the first alphabet is a C. Okay, so in this case, since the first alphabet is a B, okay, so the distance must be measured from the center of this particular rectangle towards the point B. So this give us equal to 2 meter. So this is 2 meter. Okay, so and this is basically is a X bar. and this is the area. Okay, so this is the area where this is a 250 over EIBC multiplied with the 4 meter. Okay, so simplify this, so you will get this equation, and by substituting the pressure rigidity value, so you will get that the displacement at point B is equal to 2.5 millimeter. Okay, let's proceed at the point C. Okay, so at the point C, we have defined that delta C is equal to TCA. Okay, so meaning that the limit is from C to A. Okay, that's on this one, general equation AB. So, but in this case, we have seen that this is about as point C and A. So, by looking the MEI diagram, the C to A is covered for the entire MEI diagram. So meaning that the total area that you need to consider for this case is both of this particular rectangular for AB and BC. Okay, so and that's why you can see that they have two terms. Okay, the first term is for AB, the second term is for BC. Okay, so let's look in detail on the first term. Okay, so at the first term you can see that this is area. And this is X bar. Okay, so 250 divided by EIBC multiplied with the 4 meter, so which is the area for the AB, okay, rectangular A to B. And the X bar basically is measured from the center of this rectangular towards the point C. Okay, so okay, this is the center of ABC, rectangular ABC, towards the point C, which is the distance between this center of this rectangular shape towards point C is equal to 4 divided by 2 is equal to 2 meter plus with 3 meter. So in total, the distance is equal to 5 meter. That's why you can see that here it is 5 meter. Okay, let's look into the second term. Okay, the second term is referred to this particular rectangular area. Okay, from B to C. So the area is 500 over EIBC. The height it multiplied with the 3 meter, the base of a rectangular. And X bar is referred to the distance between the center of this particular rectangular towards the point C again. Okay. So you can see that the distance is 3 can be obtained by divide the 3 by 2. It's a half of this particular rectangular base. So which is equal to 1.5 meter. Okay. So and further simplify this equation, you can see that the displacement at point C is equal to 9.06 millimeter. Okay. So that's it for this sessions. So we will continue the next sessions on the example 3 and example 4. So thanks for listening.